Hi there, and welcome everyone to my presentation. I'm going to talk about behavior trees today, and since this is the programming track of AltDev Conf, I figured it was a good opportunity to dig into some core programming issues of behavior trees. So there's been a lot of discussion in the past of behavior trees, but I think what's really missing is a good programming tutorial. So I thought this was a good opportunity to really dig into the coding side of things. So here's an example behavior tree as a teaser for what we're going to talk about, and as you can see the standard survival, combat, or relaxed behaviors that you'd find in a first-person shooter, for instance, from left to right being higher priority to lower priority, and from top to bottom being higher level behaviors, whereas at the bottom you'd have really low level and atomic actions and conditions. And we'll talk about all of that. But for this particular presentation, I'm going to show you 4 different prototypes. And the first 2, which I'm calling A and B, are first generation behavior trees. And I'll start with A, which is the simplest, and then B, which is something a bit more production ready. Then we'll talk about 2 other prototypes, which I can consider second generation. And I'll explain what all this means, just to give you structure of the talk. And we'll talk about those in the second part. So the code, we'll be open sourcing it a bit later this year on GitHub, but you should be able to retype everything from this recording or from this presentation, depending how fast you type. And you'll be able to reproduce everything just by looking at the code itself. And I highly recommend you type a behavior tree or program it yourself. It's a very good way to learn, and it's something that you really want to know the internals of rather than using an open source library anyway. But if you do want to get access to some code, then we're going to make available what we have now as a starter kit, so you can go and grab a copy on AI Game Dev. If you remember, you'll get that fairly shortly. We'll be posting it later today. So as a thanks for those of you that support the site. So in part 1, as I mentioned, I'm going to talk about first generation behavior trees, and in part 2 I'll talk about second generation behavior trees, and then we'll have a quick discussion about what's next and questions at the end. But first, I'd like to dig into some of the motivation for actually listening to this talk and for using behavior trees in practice. And behavior trees are really everywhere, and that's really the big motivation for you being here. Probably you want to find out more about what behavior trees actually are, and they're used in games like Halo ODST, Halo Reach, Spore, Dark Spore, even Red Dead Redemption uses forms of behavior trees, and many other games that go way back. And behavior trees are being used in many more systems as well. Things like character AI are the traditional use of behavior trees, but we're seeing behavior trees applied in other places as well. Just like scripts or state machines are extremely flexible, we're finding behavior trees are now very suited to other things, like in-game tutors, camera logic, player avatars, and so on and so forth. So we're also seeing behavior trees in lots of different engines. Some of them are built in, but most engines are easily extended with behavior trees. But ultimately, the reason you should look into behavior trees is because behavior trees are really awesome. And they're, as far as I'm concerned, the best of finite state machines, and then they're relatively intuitive, and they have good reactive control that responds well to the world. They also behave in a goal-driven fashion, in the sense that they're a reactive planner. That's what they're called in industry, which gives them that goal-directed, purposeful behavior. And they also provide the best of a scripting language in a very top-down fashion, and you can integrate them easily into most game engines, and they're super flexible. So I've talked about all of this stuff before, and you can download the presentation for free on AI Game Dev. It's behavior trees for next gen AI. It's a conference that I gave at GDC Europe 2007. So you can get access to that online as well. So the reason you should listen to me in particular talk about behavior trees is that I love behavior trees. I worked on them when I was at Rockstar back in 2004. I started working on behavior trees, and on Max Payne 3, on the very early version of that, we started using this behavior trees. And since then I've worked on games like Killzone 2 and Killzone 3 on the bots. Guerrilla doesn't use behavior trees, but they use hierarchical planners, which is an extremely similar technique in practice. And apart from those commercial systems, I've also written a bunch of open source code which you can find online. Game AI++ is available in the AI Game Dev forums. It's an experiment. It's quite advanced stuff, and a more basic Python implementation, which is on sourceforge.net, as the AI Sandbox, which AI Game Dev members will be familiar with, and the starter kit, the behavior tree starter kit, which I'll be showing to you today, and which will be open source later this year. So all this experience kind of helps when you're building behavior trees, but ultimately we'll be drawing from lots of different games and presentations. So over the past 3 years we've been doing interviews every week, and behavior trees is a topic that comes up most often. So in this following presentation I'm going to draw from all these different games, and we'd like to thank all the developers of all these games for contributing to the field and really sharing their thoughts as well. But when I talk about the difference between first generation and second generation behavior trees, it was really a turning point in AI for shooters and combat games, and that was the Paris Shooter Symposium that we organized last year. And there was a very clear trend and a very big difference in the trees that had been implemented before and those that were currently being implemented in games like Hitman Absolution, Ghost Recon, Future Soldier, Bulletstorm, and others. We saw clear patterns there, so that's where I coined the term first and second generation behavior trees. And the real reason for that is that behavior trees are changing fast, and the implementations have changed, partly because the way we're using them in design has changed completely. We have much deeper trees, so layers and layers of decisions that build up, and behaviors that are more complex, trees that are wider, so there are more options to choose from. We have many more leaf nodes in the behavior tree, more types of actions, more types of conditions, and a lot more NPCs as well. So this means that basically the first generation implementations of behavior trees are really struggling, and if you implement a naive behavior tree, then it will collapse under its own weight when you throw more data at it. And the second generation behavior tree can be summarized as rethinking that particular implementation to provide an efficient implementation on modern consoles in particular that will cope with those design requirements that I just talked about. So now I'd like to give you a quick introduction to behavior trees. So that was the motivation for listening. And first thing to understand is what is a behavior. And behavior can be pretty much anything from all the way from the low level, like you doing a melee attack with a weapon, or engaging in combat at a high level. Things like shooting and missing, using a smart object, dodging, rolling, dying theatrically. These are all types of behaviors. You could also consider a behavior like a condition would also be a behavior, like am I in cover, am I under fire, do I have any ammo, is the player visible? These are also, in a sense, types of behaviors that are read-only and just gather information from the world. So we have a clear distinction between actions and conditions, but they're both types of behavior, and that's a useful mechanism to have. That means we can plug together actions and conditions into the same trees and combine them together easily. So let's take a look at some code now. So I'm going to show you the first implementation, and as I said, this will be made available later this year, or you can type it in yourself based on the recording. I highly encourage you to do that. So the basis of all of this is ultimately a behavior class. And a behavior class is ultimately going to be either an action or condition or some kind of branch in the tree. And what defines a behavior is that we have an update function, which is called every frame, and we'll have an initialize function, which is called only the first time before the update is called, and then a terminate function, which is called once the update is finished, and we'll pass the status to that. So this is pretty standard interface, and those of you that have written a state machine might be familiar with it. But the big difference between this and a state machine is the status. The state in a state machine doesn't have a return status. It doesn't know whether it succeeded or failed. But in a behavior tree, you know that. So this is the important distinction between a behavior tree and the state machine. And there are many different ways you can take into account successes or failures and combine behaviors that succeed or fail together. And in general, you might experiment a little bit with different return statuses. You might try having multiple different failure codes, ones for expected errors, one for unexpected errors. But ultimately, I keep coming back to this particular design because it's such an elegant approach, and that's what turns out to be the best. So if you're not sure where to start with these 3 return statuses, and then 1 which indicates that status has not been initialized. So if we go back to the behavior now, we can take a look at a helper function, which is useful to have. Again, if you've not built behavior trees before, this is a source of bugs. Quite often you'll see, and this tick function is essentially a helper wrapper function that helps make sure that we call all our functions correctly. Things like onInitialize is only called when the behavior was not initialized first, and then we call the update function to set the status, and then if that behavior is no longer running, then we know it's terminated. So this has it's a bit of a layer of indirection, and it's not as efficient as it could be, but it will prevent many problems if you're getting started with behavior trees. And there are ways around it. We'll show you a bit later some ways to do that. So this is in fact a test file. So everything's unit tested, and that's another tip that I'll give you, is that you should be really unit testing all of your behavior tree. You don't want to be facing problems at the core of your behavior tree logic when you're debugging an AI bug. You want to know for sure that it's some complex interaction of other systems that you don't have control of. You don't want your bugs to be in the core of your behavior tree. So this is pretty standard test behavior. I'm not going to spend much time explaining this. We have measuring the number of times each function is called and capturing what the behavior returned and forcing a certain return status. So that's pretty trivial test code. And these tests will test that the initialization is called correctly and so on, and the update is called correctly, and the terminate is called correctly. And these tests may look trivial now, but as we build up complexity and we start optimizing things and introducing more performant versions, they're good things to have because we know that then our basics still work. So that covers the low-level behaviors. I'm going to switch back to the slides now and talk about how you combine those behaviors together. And the magic is that we take our primitive behaviors, or the leaf nodes in the tree, like actions and conditions, and then layer them. So a more complex behavior could be doing one behavior then another, or picking between 2 alternate behaviors. And most trees will be a combination of 2 things. There'll be sequences or selectors. So a sequence is a list of statements or a list of behaviors, in this case, that executes one by one in order. And the selector is a behavior that picks one of its possible children. Now, those of you that have a background in computer science will be reminded that most programming languages are fundamentally based on sequences and conditional branches. So behavior trees have all of that power in front of them as well. And so that gives us basically a lot of room to implement all the behavior types that we want just with these 2 types of nodes. And all the code I'm going to show you focuses on those 2 types because they're really the most commonly used. Even if you do implement custom nodes, you'll find that the sequences and the selectors are the ones that come back the most often. So let's take a quick look at what a composite is, and literally a composite is going to be an array of behaviors. In this case, I'm using a standard vector, and that's basically all it is. And then a sequence will be a type of composite behavior. I'm going to explain sequences a bit more visually so you can see what it's supposed to do first. So this is how I represent a sequence visually, and I use this notation. I introduced it in 2007, but it's inspired by some research done in hierarchical task networks. So it's a common notation that academics use, and people have adopted this notation for behavior trees as well, so I encourage you to use this notation as well. And the sequence will basically execute its child nodes from left to right. It's quite straightforward. So what we do is we deal with success of the child node by moving on to the next node, and if a failure happens, then the sequence fails as well. And if success happens all the way to the end, then that sequence will basically succeed. If a child node stops and pauses and starts processing in the background, then that sequence will continue processing as well. So it doesn't have to execute in one frame, it can execute over multiple frames. So let's take a look at how that code looks. And in this case, we're going to use the onInitialize function to set the current child to be the first child, the beginning of the list. And then we can dig into the update function. The update function says, well, I'm going to check the current child and update it. And if the child either fails or it keeps running, then the sequence fails or keeps running. Otherwise, if the child succeeds, then we go to the next child in the list, and if we hit the end, then we succeed. Otherwise, we just keep on looping until there's a child that keeps running and updating. So it's relatively trivial code. It takes 20 lines of code, and that's with a lot of comments and blank space to make the code look nice. But ultimately, it's not very difficult at all. So there's a test here again. I highly recommend tests for this kind of logic as well. And the test allocates a fake tree of a certain size. Here you can see the code. I'm not going to explain this too much. It's quite trivial code, and frees itself. And then we have a wrapper which accesses the behavior of the node type as a helper function to make the tests look a bit more simple. And in this particular case, we're allocating a sequence of size 2, and then once we're ticking the sequence, we expect it to be running. And then if we force a failure at the low level, then we expect the sequence to fail as well. And we check that the termination and the initialization of the next behavior match with what we expect. So I'm not going to talk through all of the tests, but those are the kinds of tests you need to have 100% code coverage, which is super useful to have in this particular part of the code. Now the selector logic is the complement of the sequence, and the sequence is essentially, selector is essentially represented like this as a question mark that picks one of its child nodes. In this case, we have 4 child nodes, which will be picking one of them. And there's a sense of priority in these selectors as well. From left to right, we have the first, second, third, fourth child, and the first child will be tried first. And whilst the children are failing, we'll continue to try and find the child that succeeds. And when the child succeeds, we return that child. And if no children succeed, we return a failure. So it looks very similar than the sequence, but with the status codes flipped around. And in fact, the code is basically just that. It's the same loop, except instead of checking for success, we check for failure and return failure here. So it's the exact same logic. So as an example, let's take a look at how we tick through the tree. And the first update will start at the root node, and this root might be, just a behave node, general behave in the world. And here we might have a branch for survival, and we'll have all of these branches in the tree, which will be selectors or sequences. And a very common pattern is to find alternating layers of selectors and sequences. Typically, you'll find more selectors at the top of the tree, since there are more decisions being made at the top and there's more flexibility. When you get to the bottom of the tree, there are more sequences that constrain what you can do to make sure that there are no silly behaviors or things that look out of place. But generally, there'll be a nice mix and balance of sequences and selectors. And each of those will get ticked as we update the tree until we find a leaf node that's currently running, which will be in action. And then we'll go back up the tree again. And the next frame will do the same thing. And so every time we traverse the tree right from the root to find the leaf that's currently active. So this particular prototype is basically the simplest thing you could do and still call it a behavior tree. And this is the reason why I showed it to you, to make sure that you understand what a simple behavior tree looks like. But there are a couple of things missing to take this kind of code into production. And the biggest thing that you'll consider is structuring the tree to reduce memory. So if you use code that I showed you, you'll need one individual tree for each NPC. So you'll need to duplicate a lot of data. And so when I say a lot of data, we're not talking about megabytes. It's literally just kilobytes, but that can add up quickly. And if your designers or your graphic artists want to compress their textures a bit less, then you'll be asked to reduce your memory budget to the minimum. So yeah, this kind of stuff you'll need to implement to save memory. So the answer to this is to separate the behaviors into two, and I separate them into nodes and tasks. And nodes are basically store the common data for every tree, and that's the basic structure of the tree, and all the parameters and other types of configuration that's shared by everyone. And then the tasks are basically all the runtime specific information like pointers, counters, and other stuff that only depends on the execution of the tree. So I use the word task based on cooperative tasking, or it could be microthread, or any other term like that is a good name for this, so you understand how this works. So parts of the tree will be expanded into these microthreads or these tasklets, which are currently active. So let's take a look at the implementation of this when we separate out the two types of data in the behavior. So we have a node class and a task class. And a node, basically, this is the base class for all types of nodes, and they don't do anything except just provide a way to be executed. So we need to know how to execute a behavior in the tree, and to do that we need to turn it into a task using a create function and a destroy function. And so different nodes will create themselves in different ways, but ultimately as long as you can return a task to execute, and it doesn't matter how that works. The magic will happen when we have composite nodes or branches in the tree. That's when things get a bit more interesting. So a task looks very similar to a behavior that we had earlier. We've got this standard interface like an update function on initialize on terminate, and basically a task will be initialized with a pointer back to the node that owns it, so you can access whatever data was stored inside this node. So that's pretty simple. We have a node class and a task class, and then we can combine them together back into a behavior like we had in the first prototype. And the behavior is essentially a task in the node, and then we can store the return status here as a convenience. So there are a bunch of default constructors for setting all the tasks and the nodes to null, and a shorthand notation for attaching a behavior to a particular node and initializing everything. The magic happens, well, actually it's relatively simple here. We have a task that was created from that node during the setup, and then whilst we're tearing it down, we destroy that task. And that basically means that we have a task that we can run, and the tick function that we had in the first prototype now becomes this piece of code here that asks the task to initialize itself and asks the task to update itself, and asks the task to terminate itself depending on the return status. So one thing you'll notice here is that we have an extra layer of indirection, and that's not ideal, I guess, in terms of efficiency of the code, but it's hard to avoid. If you're trying to share data, you will have some layers of indirection here, and that makes for, I guess, an interesting performance test to see which platforms work best with using more memory but less indirection versus less memory and more indirection. Yeah, in general, most developers actually use this level of indirection because it saves memory, and consoles having such a limited memory usage, you find that this is a more useful pattern, even if it does take a little bit longer to run. And so the behavior has a helper function that helps access the currently active task, and so on. But you don't necessarily need this, it's just for the tests. So now we have a test for this particular code too, and it's the same as it was before. We're counting the number of functions that were executed, and here we have we're creating a new test task. So the difference now is that when we set up a tree, we'll set it up as a node, and this could be a root node, and then when we want to execute that, we have to wrap it into a behavior, and that behavior then we can tick it, and that will essentially tick the whole subtree. And then you can see why, as things get more complex, these tests make more and more sense, because we've got more levels of indirection, and we're adding a bit more complexity into the code. And the next two prototypes will benefit from these even more. So I mentioned the magic was in the composite, and the composite node actually is just like a composite behavior. It has more nodes that it refers to, and the sequence will look very similar than the sequence in the previous piece of code, except we have to use one layer of indirection to get the node, and then fetch its children, and then initialize them. So it's relatively straightforward, and this is basically what you'd need to implement a production behavior tree to reduce the memory. So you can apply these behavior trees to 20 NPCs in parallel and not have 20 copies of the same tree. You'll just have a few tasks that are lying around in memory and that get freed relatively quickly. So the advantage of these two implementations, and I've grouped both of them together because they're basically what I consider a first-generation behavior tree. They're simple to implement. It takes relatively little code. So if we go back to the slide, there's 460 lines for the behavior tree and the unit test. So it's a relatively simple piece of code. You can debug it in Visual Studio. You can put your breakpoint inside your sequences, your selectors, and you can see exactly who's calling who and what the hierarchy is. It's relatively simple for everyone to understand. I managed to explain it without taking too much time, and I hope it made sense. And this kind of implementation will help you narrow down the API and the general specification of your behavior. So I mentioned that this is something you might want to iterate over the status codes. And, this is what I found to be the best combination of return codes. And you might want to establish a really clear calling convention for these functions as well. And having simple code helps you do that. But in general, this type of behavior tree is like having a BT pattern for C++. So we're basically structuring our C++ code in a way that's behavior tree or AI friendly. It's not really anything else beyond that. Disadvantages of this approach, as I mentioned when I showed the example, is that it's based entirely on polling. You start at the top of the tree and you will tick through the whole tree every single frame, or 5 times per second, depending how often you update your AI. And that's a whole chain of virtual functions, and you touch a lot of different memory every time you traverse the tree. And worse, if you have a behavior tree that's set up based on an XML or Lua script or some other data file, that tree will depend on the stack size will depend on the size of the tree. You can basically run into trouble if you're a designer specify really large trees. So that leads us into part 2, where I want to talk about second generation behavior trees. So the big motivation for the second generation behavior trees, or the approach that we're going to take to deal with all of those problems and performance problems, the design requirements, is to write a specialized interpreter. A specialized interpreter is something that will process our behavior tree better than C++ can. And so those of you that have experience in optimizing code will be able to do a better job than the naive C++ code that we've written in the first 2 prototypes. And generally speaking, there are a couple of ways you can approach this. First one is using brute force, and the second one is using domain knowledge. So the brute force approach is to use a data-oriented approach where you basically apply your optimization skills to this behavior tree problem. You try and account for every possible bit, reduce your function calls, make sure you craft your entire access to memory very carefully. And the second approach is to use more of a domain expert, someone that understands AI and how a behavior tree is used, and try and optimize the actual algorithm itself so it doesn't do as much work. And even if it does do that much work and it's implemented less efficiently, then it will do a better job of it. I'm going to show you a prototype of both of those things. The first is the data-oriented implementation. And this is something that game developers are now using increasingly, and that's what we saw at the Paris Shooter Symposium this year, that games like Hitman Absolution, Bulletstorm, and Crysis 2 are using very data-oriented behavior trees that execute very efficiently. They still run from the root node every frame or every time the behavior tree needs to be ticked, but they do so in a very efficient way. So there's 2 things we're going to do. First is nail down our memory allocation, and so quite obviously we'll use a stack allocator for that. And we'll allocate each node in a continuous buffer of memory, and the good default policy is to use a depth first order for storing the nodes. And I think there's room for research here. I think occasionally switching to breadth first might help, but that's something to experiment with. but just the fact that you're putting everything in a small block of memory will help a lot. So what this means is that we know that child nodes will come after their parents, so that means that we can do a lot of clever tricks to access the child node. So the big motivation for this is to reduce the number of cache misses and basically make things more memory efficient. So I'm going to switch to the code. So the behavior actually doesn't do anything differently in a data-oriented implementation. We have the exact same code as we had before. The only thing that changes is that we have a central behavior tree which will take care of all the allocation. So in this case, I'm setting a maximum limit on the nodes in the tree. But the behavior tree will basically be it's a stack allocator. And I put it here to make it self-contained, but if you have a stack allocator, you should probably reuse that. So it allocates and frees the memory, and then all the nodes inside there will be allocated one by one using placement new in the right place, and then we return that particular node. So in this case, the code wouldn't very elegantly deal with overflowing of the buffer, but it's a good exercise for you to do at home. So the tests will in fact look very similar. The test behavior is the same thing. Now we have a central behavior tree that we have to allocate for each instance of our tree, and in this case we have to allocate each node via the tree, which is relatively easy to do, and the tests unfold in the exact same way as they were before. So these tests will catch any problems you have with your allocator if you run them repeatedly. So what's interesting is that when we start building up trees and using composite nodes, there are things like sequences and selectors, and the tree will have to access their child nodes, and we don't necessarily need pointers anymore. We can use a relative offset from the current location in memory to access the child node, and it's relatively easy to jump to the child node knowing that it's located after memory. And by not using pointers, then we can save a lot of memory. So if you're using 32-bit pointers, you might save too much memory, but if you're using 64-bit, that can be quite a gain if you then drop down to 8 bits or 16 bits instead. And this is how the composites will now look. So this is the base class for the sequences and the selectors in the tree. Now each composite needs to know about its child nodes, and then we're basically storing the difference between the two pointers, the current pointer and the child pointer, and then we're storing that inside an array of offsets, relative offsets from the current location. So we can add those pointers, those offsets into our array. And likewise, and for retrieving a child behavior, we can get the pointer, and well, we can get the pointer based on the current location in memory plus the relative offset, and that gives us the actual behavior object in memory. So here we've limited the number of children to 7, which is a pretty good amount. It's quite rare to see trees that are bigger than that, and if you do, you can split them up into subsequences or sub-selectors without actually breaking anything. So in this case we have 16 bits for each offset, and potentially that could be even smaller, and we have another 16 bits to store the number of children. But you could compress this further down depending on how your behavior tree is used in practice. So if we look at the sequence now, it really doesn't change so much. The big difference is that we have to call a getChild function, which essentially looks for the behavior in memory after the current node. So we basically dereference that, but luckily we've hidden all of that logic inside the composite. So the sequence doesn't look any different than it was earlier, and it is about 15 lines of code. It's still not very complex, and we've hidden all of that complexity. So that's one of the nice things about this particular approach, is that you can apply it relatively transparently to your code. If you have an existing behavior tree, you can bring it into the world of data-oriented programming relatively quickly. The selectors are exactly the same, so I'm not going to talk about those in further detail. So the benefits of this approach is that it's not particularly difficult to implement at all, and that's a good thing to have. You just have to apply a pretty standard optimization wisdom to the problem, and you'll get good results. One thing I didn't talk about is allocating tasks and nodes. So if we have a behavior tree that is split up into the structure of the tree and the runtime data, then a good thing to do is to allocate your tasks with a pool allocator. So here we wouldn't call new, we'd get the next bit of available memory from a standard pool of memory available just for this task. There are probably slightly better things you could do to make this more memory efficient, but just having a pool there is probably good enough for most cases. The disadvantages of this approach is that it's a bit harder to debug, and yeah, you have to really iterate over the code to make it look normal. It took a couple of iterations to make the code look good, but now I guess you could just copy what I showed you and apply that straight to your behavior tree. Now let's look at my favorite example, the event-driven behavior tree. And I like this approach because it's very elegant and it really captures the minimal amount of work that you have to do each frame to update the behavior tree. So during the first traversal, everything will happen as before. So we'll arrive at the root node and then we'll expand the nodes one by one, for example, down this tree. And then when we hit the leaf node, it starts executing, and we'll again bail out of all those nodes. And the second time around, we can just jump straight back and say, well, this is the currently active behavior. All the others are just waiting for this one to finish. So I can update this leaf node, and that's sufficient. And once that's done, I can report the result back to the parent, and the parent will make its decision locally and say, well, I don't need to go all the way back up the tree, I just need to execute my child node. And so we're doing a very minimal amount of work, touching a minimal number of behaviors, which obviously is very good for memory access. Okay, so let me show you how the code looks. And the status codes are the same, except we've got the opportunity to insert an extra status code here, which is suspended, and which will say that this behavior is active, but it doesn't need to be called because it's waiting for something to happen. So this basically gives us our performance. Even though we might not use a data-oriented approach, event-driven trees can outperform data-oriented ones because we have this status code here. And the bulk of the magic will happen by a behavior observer. So each behavior will have its own observer. Or if you're splitting up your nodes and your tasks, then each task will have a task observer, which will notify its parent that it's done, and the parent will be able to deal with that as it sees fit. So now our behavior tree class becomes more of an interpreter. So its job is to pass back all these events back and forth throughout the tree. So we need to basically insert an active behavior into the tree and say, well, I will add it to my queue of active behaviors, so I'll push it to the front of the list and set the observer if necessary. And then I have a way to forcefully terminate the behavior as well, so I can set its result status. That's useful for parents to forcefully fail a certain node or fail themselves. So those are the two ways we can insert active behaviors. And then the main entry point of the behavior tree is a tick function that will loop through all of the behaviors. So what we insert is we use a marker in the list of behaviors that says, well, this is a placeholder that says that we finished a current update, and so we don't have to keep looping. So whilst we haven't found the marker, we'll keep single stepping through the behaviors. In this case, I use a deck, but you could use a list, or I think use a vector as well. We have to implement it slightly differently than I showed you, but it should work equally well. So the single stepping and this is where the magic happens. We take the next behavior from the front of the list, and then we pop it off the front of the list. And if we found that end of update marker, then we know we're done. So this step function returns false, and the update of the whole tree is finished. Otherwise, then we know that we have an active behavior still, and we can tick it. Then if that behavior is terminated and we have an observer, we call the observer to notify its parent. And if the behavior is still running, we can push it back into the list for updating the next frame. So if we took into account our suspended code, say if we're not suspended, we'll put that code here, and that would save us calling the tick function if we don't need to. Okay. So the rest of the logic looks very similar. We have standard tests here again. And the big difference here, once we have our behavior tree, we have to insert it into a tree and then tick it. And that basically runs our code for us. And likewise, a lot of the complexity of this particular implementation happens in the composite nodes. They look similar structurally, but the logic is completely inverted. So let's take a look at the sequence as an example. And then we have an initialize function which inserts the current behavior into the tree. And then we have a node that's set up based on child complete, which will get called once that finishes. And then if the child has failed, we terminate ourselves with failure. If the child succeeds, then we go to the next item in the list. And otherwise, we add the next child into the behavior tree. And that gives us an awesome event-driven behavior tree. So that covers event-driven behavior trees. And what I love about this is that it guarantees that you have a minimal amount of work being done every frame, and you can build a single-step debugger using that step function. It's pretty awesome. And it's a nice, elegant approach. Not many people are using it, so you get thrown as geek points for that. The disadvantage is that potentially your code looks like it's inside out, but you get used to it, and in the way the code I showed you today, it's relatively straightforward to understand. So I'll just quickly, in the last couple of minutes, just share what's beyond in terms of implementation. So there's a couple of things that I didn't cover. Things like decorators, which are composite nodes with single children, filters, and parallel nodes. Those are a couple of concepts that you might need. I didn't have time to cover them today. But generally, the only thing that's left is to say what implementations we'll bring in the future. And that is basically combining this data-oriented approach with the event-driven approach. And I haven't written one, but that could fit in this fifth tab here. And most games will use either implementation E, which is a data-oriented version with shared code. There's some code that uses an event-driven approach, but ultimately we still quite haven't seen the combination of the two. And I think that's the future. Which should leave me just in time for questions. Hopefully that wasn't too long, Wolfgang.
No, it's wonderful. Thanks a lot. So we actually have 2 questions, and I just sent you one. Can you see it, Alex? Alex?
Yeah, I can see it.
Okay,
do great. Any good commercial behavior tree implementations?
I can.
That makes sense.
Should I read it?
Yeah, you can repeat it if you want. Yeah.
Yeah. We get actually more questions now. So Alex, do you know of any good commercial BT implementations? And does it make sense to look for them? For example, if they come with great authoring tools, etc.
So my take on commercial implementations is that they're still relatively recent, and there's a couple companies that are starting to provide that kind of technology, but I think it will take another year or so for them to be more established. I highly recommend you implement your own behavior tree, because I think you need to really have ownership over this kind of code. This is something you want to know as an AI programmer. If your behavior tree comes with a user interface that allows you to do single stepping, like I showed here, if this step function is hooked up to your user interface, then I think that's worth paying for. And I don't know many that do this, but I know there are a couple middleware libraries out there. One of them is for Unity, and another one is more platform general. Yeah, in general, I do recommend writing your own at this stage, but I haven't evaluated many user interfaces recently, so they might have improved a lot. I'll certainly take a look at the more recent offerings.
Okay, so the next question is, how do you handle contingencies for when your hand-authored priorities are not applicable for all possible situations? That is, what if B needs to be tried, sequenced, before A given context acts?
Okay, I think that's more of a design question rather than an implementation question, but I'll take it quickly. I think if you have dynamic priorities, I don't know if that's your question, you should probably split your behaviors into two, and there's a good way to do that. Basically, if you find that a retreat into cover behavior is applied in two different contexts, then you'll insert that behavior twice in the tree at different prioritization levels. So that's typically the best way to do it, so that you can have dynamic priorities by essentially having two static priorities that switch between each other, if you see what I mean. Yeah. Any other questions?
Yes, there are more. I'll send you another one. Alex, have you measured statistically, or do you plan to, the computational improvement achieved with these new implementations? It would be interesting to see something like that as a motivation for someone to program them in this way, despite of its higher complexity.
So I haven't measured the complexity of this particular code, but as soon as you write this on a console, you'll notice a really noticeable speed improvement, and that's why most of the game studios have switched to data-oriented implementations. So famously, Crysis 1 was implemented with behavior trees that were mostly Lua, and that was extremely slow, and they went to a highly efficient C++ implementation for Crysis 2, and well, it really suffered was they still had that Lua-based implementation, so they absolutely had to upgrade. And I'm expecting that they saw multiple orders of magnitude speed improvement over a scripting language. As I said, I haven't measured the performance of this code, and hopefully we'll be getting our hands on the dev kit here at the AI Game Dev Labs, so we can measure this code on the PS3. So I haven't done that for this particular instance of the code.
Okay, next question is, if agents are running the same BT structure, won't they all act exactly the same as each other? How do you generate variation in behavior between agents?
So this is a standard problem not just for behavior trees but for AI. If you have a standard AI that's applied to different agents, what makes it different on the different agents? And basically it's because you insert a complex system into a particular point of the environment, it will behave differently because the environment is different. So that's the basic answer, is that your environment will require different behaviors from your behavior tree. So the results will look very different because the behavior tree is adapting to what is there. So that becomes a very dynamic, adaptive behavior tree that deals with different situations for different characters. I hope that answers the question.
Okay, next one is, usually what's the memory budget for, I think it means for these behavior trees?
Well, in general, you can measure the size of each node, and we're talking something between like 16 bytes sometimes to maybe 64 bytes, 128 bytes. Some nodes are bigger than others, and the size of the tree overall could be between 100 and 200 nodes. Some are even bigger. I guess first generation trees are much smaller. We're talking 40, 50 nodes. So in general, we're talking kilobytes, and there's really not that much memory that's taken by these trees, especially if you store the common data in one single point. So I hope that answers that question too.
Mm-hmm. How do designers implement actual game logic using BTs? Are there any visual tools or scripting interfaces?
So generally, behavior trees are implemented mostly by technical designers or programmers, and there's been a big discussion whether behavior trees should be used by designers, but in practice we find that it's programmers who end up doing the work because they're more technically minded and because it's going to be a nice piece of self-contained logic that it's not huge. It's manageable by 1 or 2 programmers. So programmers tend to do the work. If you find a highly technical designer, I was lucky enough to work with one at Rockstar, and he took over a lot of that stuff, but I would still build the low levels of the tree, and he would build the higher levels. I've seen designers or programmers do this with text editors, which is a good place to start, but you can write a fairly simple behavior tree editor yourself using a standard tree widget, or use one of the commercial systems if there are any available.
Okay, next question is, with the event-driven tree, how do you handle reactive conditions higher up the tree? Keep them running in a parallel node?
Yeah, that's generally the pattern to use. I call that monitoring. So when you have a behavior that needs to monitor its assumptions, you will have a condition that's running in parallel, and that will constantly be checking, am I under threat? Am I under threat? And if that's the case, then you'll stop going to pick up a bonus item, then bail out of that behavior and deal with that by going into a different branch.